So hello everyone, welcome to your second class of Physics 1. Basically we went through the syllabus, it's a little bit about algebra, but I'm going to just jump in. Once again, this first chapter isn't really physics, it's all just math stuff we need to all know and be on the same page of to move forward. So yeah. This was the last slide I showed, and I was talking about how you have tiny ass numbers or really big numbers. They're annoying as hell to write, and we were going to use scientific notation. I actually ended on this slide. And so I'm going to pick up right where I was and say, hey, let's learn how to do this. Here's the general idea. When you want to put a number in scientific notation, if you're taking from the initial number, as in regular, if you're starting from one of these and you want to go to one of those, the general idea is you count how many spots you need to move the decimal to get it one away from the end, to get a number between 1 and 9.9 repeating. If I give you this 65 million, if you want to put that in scientific notation, you'll just count how many spots you need to get the decimal to get it one away from the end. And you can see if I have the 65 million, I have to move it 7 times to get to 6.5 times 10 to the 7th. You could also use the same logic to go the other way, that if I say 6.5 times 10 to the 7th, I can just say move this decimal 7 spots. It's a positive exponent, so it'll be a big number, 1, 2, 3, 4, 5, 6, 7, and say it's the whole same 65 million. I am so good at writing on the screen. This is why I have a dot cam. I should be using that. If it's a negative exponent, it's the same idea. If you have it in regular notation, you want to put in scientific notation, just count how many spots you need to get the decimal to get it one past the first non-zero digit. In this case, this number right here would be 9.87 times 10 to negative fifth. Negative because it was a small number, and 5 because I had to move the decimal 5 spots over. Same idea though, you can go in the opposite direction, that if I want to put this number in from scientific notation to normal, I would just start with 9.87 and say 10 to the 5th, 1, 2, 3, 4, 5, and just move it 5 spots. Here I know I'm going to the left because it's a negative exponent, so it has to be a small number. Of note, calculators do work in scientific notation, but you normally don't have to do it like this. Most calculators will have a button with 2 E's on it. Mine's probably a different spot than yours would be, but this EE, that's to do scientific notation. If I want 9.87 times 10 negative fifth, I can just type in 9.87 EE negative 5. For most of you, the count will probably be above a button. It'll be like a second hit something to get to, but that will be for scientific notation's EE button. When we're in person, I normally have people do this out loud in class, but that kind of sucks on Zoom. I hate Zoom. In-person teaching is better. But if I want to go the other way, just to show it, if I have 1.73 times 10 to the fourth, if I want to convert this, you just write down what you got, 1.73. It's a positive exponent, so I want a big number. And I just say that I'm going to move this decimal 4 spots over, 1, 2, 3, 4. And so my decimal spot's now here with these zeros. And so what that means is 1.73 times 10 to the fourth is the same as 17,300. If you're going negative, same idea, 6.78, 6 spots. I should have moved this over further. You know what? 6.78. I want to move it over 6 spots. So I just say what? Nope. Draw. 1, 2, 3, 4, 5, 6. And I can say, okay, that is 0.00000678. Now, on your homework, you will sometimes want to work in scientific notation. Vanco Hall uses the same thing as most computer programs. Excel can also do scientific notation, and both Vanco Hall and Excel use the E notation. If you want to enter a number in scientific notation, just use the letter E to represent, times 10 to the. So 6.02 times 10 to the 23rd is 6.02 E23. 1.6 times 10 negative 18th is 1.6 E negative 18. Don't include like the caret on it. Like don't put 6.02 E to the 23rd. People do that sometimes. Don't do that. Just write it just like that. This slide shouldn't be here. That's a mistake. Any questions? Okay, we're gonna jump topics entirely then, if there's no questions. So let's pretend we were in Delhi, because that's what my notes assume, and I'm in Oneonta, so screw that noise. But let's say we were in Delhi. Or I can just do it like this. I actually wrote change the wording here. And I can say it's 20 to Oneonta from Delhi. That's a useless sentence. I might mean it's 20 minutes from Oneonta to Delhi. I might mean it's 20 miles from Oneonta to Delhi. But I could also mean kilometers. It might be that Oneonta is like a star far away, and it might be 20 light years to Delhi. When you go and give a number, you always have to include units, because if there's no units, you can't interpret the number. Saying there's 20 from Oneonta to Delhi doesn't make sense until you include it's 20 miles to Delhi. In this class, we are going to use what is called SI units. SI is short for Le Système International de Units, which sounds like someone who can't speak French pretending they can and saying International System of Units, but is legitimately in French International System of Units. We must always use these set units, these SI units. And what this defines is that all length will be measured in meters. All mass will be measured in kilograms. All time will be measured in seconds. And anytime I give a unit that is not in meters, kilograms, or seconds, or some combination therein, or a few others that I'll come to in a second, you're going to need to make sure you convert. Now, this always leads to, but we're in America. Why aren't we using feet and pounds and still seconds, because we use seconds? And to that, I have 3 reasons why we're going to use metric. The first off is metric is easier to convert. There is 12 inches in a foot, 3 feet in a yard, and I have no fucking idea how many yards in a mile. However, in metric, in 1 meter, which is what I'm holding here, in 1 meter, there is 10 decimeters. Oops, wrong way. In 1 decimeter, there is 10 centimeters. In 1 centimeter, there is 10 millimeters. It's nice and simple. Everything is a factor of 10. And in fact, that prefixes of centa, deci, and milli works for meters and seconds and grams and anything else. It's easier conversions. The next thing is that this is probably the most important here, is that all of our equations are going to assume metric. I'm going to be using equations with constants in them, and the constants are in metric. And so if you're not in metric, you won't get the right answer. And since all of the equations and constants are metric, you need to be also. But the most important reason is because science is an international community. When I used to do research, I worked directly with people in Hong Kong and Taiwan and England, and we'd be comparing notes. And if you compare places that use metric versus places that don't use metric, well, we're a little outnumbered. When I put this together at the time, only 3 countries did not use metric: America, Liberia, and Burma. I think Liberia might have changed. I need to check this. I think Liberia might use metric now. The world uses metric, and America would like to be part of the world. And so it would be better if we just use the same. It's easier, it makes the math nicer. We're only not doing it because we're too lazy to change. And it's expensive. Fun fact, it actually passed Congress in the 80s, late 70s, early 80s. It passed Congress that America was going to completely switch to metric. And then there was a presidential election, and the president who took office, one of his first things was an executive order to veto it and stop it, and we stopped the process of switching to metric. But America did start switching to metric once in the late 70s, early 80s. I forget the exact years. So if we're going to use the metric units, let's do what they are. In the metric system, there are 7 base units. All metric units are derived from these 7. And all of these base units are based off physical constants of nature that don't change and so will always be the same. Length, as we said before, is the meter. Use the symbol M. It's length. I think I said light. Length is the meter. Length is defined, or meter, which is, once again, this guy. A meter is defined as how far light travels in 1/299,792,458th of a second. Mass will always be measured in grams. Well, the base unit is a gram. Well, a gram is defined as based off Planck's constant equals mc squared. I'm not going to go through the details. It's complicated. For the record, we would never use grams in this class. We will always use kilograms, where 1 kilogram is 1,000 grams. Time is always in seconds. It's based off the half-life of cesium, and is one you're the most familiar of. These are the ones we're going to be using in this class. The other one base units that you sometimes see is electric current is based off an ampere. It's based off the charge of an electron. There is also temperature. Oh, we'll be using this one too. I forgot this one. There is temperature. The SI unit is the Kelvin. It's based off Boltzmann's constant. Of note, we will also be using Celsius. Celsius and Kelvin are very similar. They just have a different 0 offset. What the hell I mean by that, I'll get into in the next to last chapter. Amount of substance is some chemistry bullshit based off the mole. We'll cover that a little bit in this class too, but it's chemistry bullshit and no one cares about chemistry. And how bright something is based off the candela. I have never worked in candelas. I have never used candelas. I know nothing about them, but that's a thing. All other units in metric will be based off these. For example, you might be familiar with the idea, I said amps was one of them, or ampere, but ampere is the same as amps. You might be familiar with volts. Volts are derived by amps. I can't do the full derivation off the top of my head without including ohms, and ohms is also derived from amps. But there's a direct link between them. All other units are just derivations of these put together. So I already said you got to label your units. It's story time. We're gonna have a bunch of those this chapter. I'm acting all excited for some reason. So why units matter? This is a thing that happened in 1999. America put tried to put a weather satellite to orbit Mars. It's going to be the first weather satellite around a different planet. And the general idea, or what happened, was there was a whole bunch of engineers working on this project. And the engineers are like, we're in America, we're using American units. And because they were apparently really fucking bad at their job, they didn't label their units. Then working on this was also a bunch of scientists. And the scientists are like, this is like a scientific thing. Science, we use metric. Everyone uses metric. It's obvious. And since everyone uses metric, we don't need to label our units. And because they were bad at their job, also didn't label their units. So what happened is the scientists assumed everyone would work in metric because everyone should work in metric, and didn't label it. And the engineers assumed everyone worked in American units because we were in America and didn't label. And they assumed the scientists must have worked in those American units too. So instead of the satellite going up and going around the planet, it went up, fired extra burners, and went full speed into the side of the planet, instantly destroying itself. $125 million gone. Because people didn't label their fucking units. This is crucial. A whole bunch of you in this room are architects. I know this. If you try to give someone an architect a plan and you decide to work in feet and the person goes to build it and they decide to work in meters, you're going to get everything 3 times as big. A number without units is pointless. You must label your units. I'll go so far as to say a number without units is just going to be plain wrong. That being said, on homework, I do require units. Anytime you put a number, there are some times where units aren't necessary. They're few and far between. You must label your units. Every time you have a missing unit, you will lose half the points for the problem. Now, of note, I've said before that on Banco Hall, it'll give a GIF or a meme every time you get the problem right. The GIF or meme shows up when the numerical value is correct. So if you do not get a GIF or meme, the number is wrong, definitely. The units may or may not be wrong. If you get a GIF or meme and it's still marked wrong, if you get a GIF or meme and it does not give you full credit, that means your value is correct, your units are wrong. Fix your units. Questions? Okay. So, since I just stressed metric, let's get to why metric is fun. I already said metric had easy unit conversions. The reason why is metrics uses a series of prefixes. I said before how going in this guy, like this upside down? No, well, it's backwards to be, but this is showing that in this little bit, which right from here to here is 10 centimeters, I have all these other little marks. What this is those 10 millimeters in a centimeter. But the thing is, there's also 10 milligrams in a centigram, and 10 milliliters in a centiliter, and 10 milliseconds in a centisecond. Metric has a series of prefixes that work for all of its units, no matter what. And while I can't tell you how many pints are in a quart with a gallon, I have no idea. Wait, I think there's 2 cups in a pint. I might know that one. I know my pints. And I know how many teaspoons are in a tablespoon. But it's much easier to say that in a liter, there's 100 centiliters in a liter. Everything's a factor of 10. And so metric will have a series of prefixes that are a factor of 10 to make conversions easier. In fact, here's the full table. The general idea is any metric unit, with the exception of deca, they will have a prefix or no prefix in the case the base unit that represents what the factor of 10 is, followed by a symbol for the unit. Those symbols being the M for meters, the L for liters, the S for seconds, the G for grams, like we talked about. And that each prefix will say give a factor. Now note, capital and lowercase make a difference. Capital M is mega, lowercase m is milli. Be careful. But what this does is this says for each prefix how many are in the base unit. And for example, if I say we have a kilometer, this has that a kilo, it has 1,000. What that means is 1 kilometer is 1,000 meters in scientific notation or regular. And I can go further. If you say you have 3 milliliters, well, 1 milliliter is 10 to the negative third liters. So 3 milliliters is 3 times 10 to the negative third liters, and so on. Good so far? I'm sure you've all seen this before. Other reason it matters, and this is a big thing for physics, if you don't know what you're doing, which is going to happen from time to time in this class, your units can tell you. In any physics equation, the units have to work in the equation. Units can enter algebraic equations just like other terms. If I take an equation and say like x pen's not really working, x squared divided by x, you can be like, oh look, one cancels, that's just x. Units work the same. Units follow just like any other variable in algebra. And if you have an equation, if the units do not work, the answer will not work. It's a great way to check what you're doing. I actually recommend when you do math, when you plug numbers into physics equations, plug your units in. If you plug your units in, you can and cancel them out, you can find out if things are going to work. In fact, there's something called dimensional analysis. Dimensional analysis is you plug your units and only your units into equation, no numbers. And you see if the values are, if it all works out. If it works out, you have a possible equation. If it doesn't work out, it's an impossible equation. Now I say a possible equation because it might be off by a constant. You might be missing a 1/2. You can't tell that with the units, but it's a good way to check. Here's what I mean an example. So length is measured in meters, time is measured in seconds, and velocity is a meter per second. We'll cover that more later on. Let's say I gave you this equation, x equals vt squared. We could see if that equation is possible or not, just by plugging in units. I don't have to tell you a value of length or time or velocity. I'll just plug in the units and say x is in meters. V is meters per second. T is in seconds. T is squared, so seconds squared. Now say, okay, let's look at this. I have meters equals meters divided by seconds times seconds squared. This seconds will cancel with this squared, and I get this guy. Oop, that's not in the right spot. That can't possibly be correct because I'm saying meters equals a meter second. That's not right. That has to be wrong. If I instead said x equals vt, I would say meters equals meters divided by seconds times seconds. Now if I go and try to cancel out my seconds, I'm left with meters equals meters. That's a possible equation. But as I said before, this wouldn't let you know if you're off by a unitless constant. But it can get you in the right ballpark. Questions? It's really easy to get used to between semesters, not talking out loud too much other than like the one person who, like my wife who lives here with me. So like talking this excited for this long is, gotta get used to it again. We good? Okay. Units aren't the only thing that's really important to keep track of with your values. When you say how the value of something, if you say, you have your units, say, okay, this is 10 meters long. There's some other stuff we got to pay attention to. And one of the big ones is uncertainty. All value time you measure something, there's going to be a certain amount of uncertainty. Let's say I want to measure the length of this arrow. And I decide to use this large meter stick. If I go and try to use this side, which has a mark every decimeter, or if I try to go and use this side, which has a mark every millimeter, I'm going to have a very different level of exactness. Where here I can get pretty close to exact. While this one, I'm guessing to the nth degree. Anytime you measure a quantity, there will be a certain amount of uncertainty in the measurement. It's traditionally written as follows. You write what you think the value is with units, plus or minus the uncertainty in the value. What this means, if I write this, is I'm saying the length of something is 0.061 meters with an uncertainty of 0.002 meters. Always your uncertainty should have the same units as the value. If I do uncertainty with symbols, I don't think I wrote this here. There's something that should be on the slide and it's not, so I'm going to cover in a second. If I do it with symbols, uncertainty we always represented by sigma, with sigma sub something, sigma x if I'm measuring x, and so on. And what this uncertainty means, what it really means, is it's a wiggle room. I'm saying that the value of this length isn't just straight up x. I'm saying the value is not 0.0061. I'm saying it's anywhere between 0.061 minus 0.002 meters to 0.061 plus 0.002 meters. or 0.059 meters to 0.063 meters. I'm saying the value is anywhere between there. Where in that range? I don't know. That's the whole point of uncertainty. It's acknowledging what we don't know. And we use this to help try to make things as exact as we can. Questions? Now, if you're making a measurement, you're measuring something yourself, you got your ruler, you're going, you're measuring a length. How to find the uncertainty is kind of interesting. If you have a digital device, the uncertainty is always the last digit because this is reading 87.93. But this could be anywhere between 87.295 to 87.934. And really I could go 87.949 to 87.9344. Like the range is off. And so any of a digital measurement, you say it's the last digit. The uncertainty here would be 0.01. If I had a digital device and it read and it showed like 20.2358, I would say the uncertainty would be 0.0001. For any digital measurement, the uncertainty is a 1 in whatever the last digit is. For an analog measurement, shit be complicated. Some people would tell you that analog measurement, your uncertainty should always be half the least count, where the least count is the smallest size marking. This ruler that I have zoomed in here is showing every millimeter, so the uncertainty should be half a millimeter, or 0.05 centimeters. I personally don't believe that. The uncertainty in an analog measurement is how accurately you can measure. I have really bad eyesight. So when I look at something with millimeter markings, I have a hard time differentiating between them because they all kind of blur together. I normally round to the millimeter or 0.1 centimeters. Anytime you make an analog measurement, the uncertainty in it is how accurate you think you measured and how accurate you are doing it. And you just fess up to what it is. It's not everyone's always going to agree. If I look at this thing of waddle, I might say, okay, let's see. So this is 50, 51, 52, 53. So it's just shy of 53. So someone might say it's 53 plus or minus a half milliliter, which is saying plus or minus, I lost my mouse, plus or minus half of one of these sizes, plus or minus that. Someone else would say, no, I can do better than that. It's less than 53. I'd say it's 52.8 plus or minus 0.2 milliliters, which is going to be a wiggle room of about that big. How accurate you measure it is up to you. But when you make a measurement, you should keep track of uncertainty. Now, if you didn't make the measurement yourself and you're given the measurement, assume the last digit is uncertainty. And you kind of already do this and don't necessarily think of it. Normally, if people have a very accurate device, they let you know. If I tell you have 4 milliliters of something, you should assume that it's somewhere plus or minus 1. That it's really somewhere between 3 or 5. Earlier I said there's 20 miles from Oneonta to Delhi. That's not very exact. When I say there's 20 miles to Oneonta to Delhi, that's just rounding. I don't know the exact measurement off the top of my head. But if I told you there was 20.0 miles between Oneonta to Delhi, you would assume it's pretty exact if I add the 0.0. And that's why you do this. Always assume the last non-zero digit is rounded. If I tell you something's 8.6 centimeters, you should assume your uncertainty is 0.1 centimeter. If I tell you 5.98 seconds, you should assume the uncertainty is 0.01 seconds. And so on, unless you're told explicitly. If you're told explicitly, then hey, you don't have to worry about it. But if someone doesn't tell you, you can make those assumptions. Now, we're not just collecting data for fun. When we collect data, we're going to use that data to analyze data and get results. We're going to be making measurements and trying to use it to find things out about the world. What that means is we're going to do calculations. And if you're going to do calculations with a number, you need to make sure your uncertainties are still used. Let's say, for example, I measure the length of something to be, we'll just use this number right here. I measure the length of something to be 8.6 centimeters plus or minus 0.1 centimeter. And that is going to be a radius. And I want the circumference. Well, if I want the circumference, I'm going to multiply by pi. If I do 8.6 times pi, 8.6 times pi, I get 27.017696820872. If I had an uncertainty of 0.1 centimeter before I did that, half those digits aren't going to mean anything. And so when you do a calculation, you have to think about how that affects your uncertainty also. Whenever you do a calculation with uncertainty, if the numbers are added or subtracted, if you have A equals B plus C or A equals B minus C, you just add together the uncertainties. That the uncertainty in A is the uncertainty in B plus the uncertainty in C. If you're multiplying a number by a constant, such as y equals cx, you can multiply the uncertainty by that constant. That if y equals cx, the uncertainty in y is c times the uncertainty in x. If you have anything else, the answer involves calculus and taking a derivative, which I don't expect you to do because this is not a calc-based course. So for anything else, I would have to give it to you. And fun fact, this is going to come up a lot in labs, and in every lab, when it comes up, I just give you the equation. I mean, to pull one up, this isn't necessarily the first lab. This is just a rant. Actually, this is the first lab. That worked well. I reached into the pile and grabbed the right one. So for example, in the first lab, you're going to be asked to find n. And I tell you that n is slope over k sub b. I'm going to ask you to solve n, and what you're going to do is you're going to find the slope using the stuff on the next slide, the things we covered last class. And we'll get a value of n, saying it's whatever your value of slope is over Boltzmann's constant. You're also going to find the uncertainty in n, because it will be the uncertainty in slope over Boltzmann's constant. I'll give equations to solve for it. Okay. I mean, this is how it gets involved in you. In all labs, I'm going to ask for uncertainty, or most labs. There's a few I don't. And if you're getting data without a graph, you can estimate it using the methods on the last few slides. But if a graph, you're going to need the uncertainty and slope. And to get the uncertainty and slope, we're going to use something called the linest function. The linest function can be done in Excel or Google Sheets. How to do it in each is slightly different. My Excel/Google Sheets tutorials walk you through the process. Of note also, I don't have Vanco Hall open right now. On Vanco Hall, there was that picture I showed. I open as I talk. There was that picture I showed on Vanco Hall from the side of the classroom. How to do the linest function. This guy is also printed here. That if you click this, it'll get real big and has linest in Excel. Oops, linest in Google Sheets. What it all means. So you can get it right from there. But I'm going to kind of show you now anyways. When you have data and you make a graph, you're going to, as I said, do this function. I'm not going to go through the process of making the function. You'll get that either here or the separate tutorial video. Do it from that. And what it would do is it'll fill full or more boxes. And what you always want to do is look at the top left two boxes. We're only ever going to care about two of the full boxes. Those two being these two right here. If there's more, still just the top two. And what it is whatever is in the upper left, that is your slope. It should be exactly the same as the trend line on your graph. And if it's not the same as the trend line on your graph, you done fucked up somewhere, figure out where, or come get help. The number beneath that is the uncertainty in slope. And that's what we're going to need. I'm always, every lab with a graph, I'm going to ask you to write down the slope and the uncertainty in slope. And I'll note that equations will show up with things like slope equals nkbt. Don't use that. That's just showing me how I got to the math to get to the equation going to be used. Anytime you have to get the slope, you get the slope by looking at your graph, the trend line and the line S function. And once you get the slope and uncertainty slope, that would be these left two boxes. I mean, just so you know, the upper right is the y-intercept, and the lower right is the uncertainty in y-intercept, but we'll never need it. And if I look at this data, this is the same data I used on Monday. I said the slope of the graph was 2.65 kilograms, if you remember. What this is saying is that's not actually true. It's that the slope of the graph, 2.66, I didn't round, is 2.66 plus or minus 0.07 kilograms. That's the actual slope with uncertainty. That it's somewhere between 2.73 and 2.59 kilograms. That's just being me adding and subtracting 0.07 kilograms respectively. Does that make sense? We good? Okay. So let's say you work with uncertainty. And I already gave this example, and I actually said the equation for the circumference of a circle wrong when I did it before, because I'm an idiot. Let's go back to this idea. I said a cat go flying through the room. You measure the radius of a circle to be 1.23 centimeters, and you measure with a certain amount of uncertainty, that uncertainty being 0.01 centimeters. And you want to get the circumference. Well, circumference is 2 pi r. So we can say the circumference of the circle is 7.72832 centimeters. But we also know the uncertainty in the circumference is 2 pi times the uncertainty in radius. So that means the uncertainty in the circumference is 0.0628 centimeters. And let's compare these numbers. If we're saying the circumference is this plus or minus that, this digit right here, that 2, is pretty goddamn useless because it's well within the uncertainty. I'd go so far as to say it has no meaning. Most of this value is C after like this 2, this 8, the 823 at the end, have no meaning because they're well within the uncertainty. And so when we do this calculation, we don't want to include numbers that don't mean anything. That if the number has no meaning, it doesn't help us at all, why bother with it? And this gets into the other idea with uncertainty. Whenever you make a measurement and do a calculation, you should keep track of how many of the digits are significant. Significant meaning they have meaning. Significant meaning they are useful. And yes, apparently the rest of today's class is going to be done with one of my 2 cats. And digits that are significant or useful are called significant figures. And we need to keep track of these. That whenever you do a calculation, you keep track of how many significant figures they are, and you round your final answer to the appropriate number of significant figures. So the first thing you got to know is how to measure significant figures. And so here's the idea. I'm going to break our numbers into 3 categories. The first one is the number is greater than 1 and has no decimal. If a number is greater than 1 and has no decimal, all of the digits to the left of the first 0 are significant. She just turned off my thing. So 1000 is 1 sig fig. 656,000 is 3 sig figs. 604,000 is 3 sig figs. What you do is you go to your first non-zero digit and count everything after that. Note, you don't just count all the non-zero digits, but you count all the non-zero digits after your first one. This only works though if a number is greater than 1 and has no decimal. If a number is less than 1, you count all things, you still count everything after the first non-zero digit, but it's all things to the right. You don't count the zeros between that and the decimal. And so this is 1 sig fig. This is 3 sig figs. If I did 0.002 2, 0, 1, this would also be 3 sig figs. And even 0.00200 is still 3 significant digits. It's everything from your first non-zero digit and beyond. However, if a number is greater than 1 and has a decimal, always count everything. This is the difference between saying something is about 1,000 kilograms versus saying it's 1,000.0 kilograms. It's assumed when the decimal is put in there, it's put in there for a reason. And we're going to break all the numbers into these categories. Greater than 1, don't count the zeros to the right. Less than 1, don't count the zeros to the left. And greater than 1 with a decimal, count it all. Questions? Okay. At this point, I'm going to ask whoever's comfortable to unmute themselves. I'm going to put up a bunch of numbers, and I want people, I don't care who, to shout out how many significant digits they have. I'm going to try to do this online like I would do it in class. So, anyone unmuting themselves, how many significant digits?
1.
1. How many?
3. 2. 2. 2. 1. 4. 5.
Got ahead of myself. Yeah. That's the general idea. If a number is less than 1, we do everything oval, hence these being 2. If a number is greater than 1 doesn't have a decimal, you count everything over there, 1, 1. And if it has a decimal, you count the whole thing. Now, if you're in scientific notation, it's always going to be easy. If you're in scientific notation, you just ignore the times 10 to the part. And you just have a number greater than 1 with a decimal. 2.1 times 10 to the 5th, that's 2 sig figs, the same as 2.1. 100 times 10 to the negative 5th, 3 sig figs. That's the same idea. But the thing is, what I haven't gotten into here is what the hell we're doing with these. It's all well and good to say, hey, these are significant digits. Keep track of them. But the question is always like, why? Who cares? Honestly, I very seldom care as much as I should. I should grade significant figures heavier than I do. I'm bad at grading significant figures because I can't bring myself to care most of the time. But significant digits are a way that when you do calculation, you do not increase the number of errors. And they're a way of saying what you do when you do algebra to things. Do algebra to things. I am good at English. And so there are set rules when you do calculations on what you should always round to. And how you round would depend on what you're doing. And basically, it's going to be addition and subtraction and everything else. Any problem where you're adding and subtracting numbers, ignore significant digits completely. And if you're adding numbers, you should always round the final answer to whichever has the fewest decimal spots. 3 plus 6.8 plus 4.21 is 14.01. But really, you should round that to 14. And the reason why is because this 3 number has some uncertainty here. And so saying 14.01 is bringing in certainty we don't have, because 3 could really be between 2 and 4 somewhere. 4.6 plus 8.7 plus 6.93, I should round my final answer to 1 decimal, not significant figures, 1 decimal, because that was what was the smallest of what went into it. But you're going to find very seldom in this class are we going to add and subtract. We're normally going to multiply and divide. When you multiply or divide numbers, you have to use significant digits. And what happens is anytime you multiply or divide numbers, keep track of how many significant figures each digit has. And always round your final answer to whatever had the fewest significant digits. 5.6 times 1.2. They both have 2 sig figs. I round my final answer to 2 sig figs. 10 times 4.6777. 10 has 1 significant digit. 4.6777 has 5. What is less than 5? I round my answer to 1 significant digit. 10.0 times 4.6777. 10.0 has 3 significant digits. I round my answer to 3 significant digits. Okay. On your homework, always use at least 3 significant digits. Vanco Hall grades by percent off. I made sure that I always did 3 significant digits. If you ever put an answer in with only 2 significant digits, it might mark it wrong even when you did it correct because the way it grades. Always use at least 3 significant digits on Vanco Hall. Now, I have been saying you got to round these things, rounding rules. I assume people use the same rounding rules as most, but I can always cover them. If you're going to round, when you round a number, look at the first digit you're getting rid of. If the digit is less than 5, you drop it. 5.7615, I want to round down. 1 is less than 5, I get rid of it. If the first digit you're getting rid of is 5 or higher, you increase the previous digit by 1 when you round. 3.9895 becomes 3.99. What I would say though, when doing calculations in this class, don't round anything until the final answer. I recommend having a graphing calculator and being able to recall numbers, or while you're mid-problem, keep as many digits as possible. If you round mid-problem, you can cause errors. Don't round until the end. The only thing really to keep track of though is when you round significant digits, make sure your number doesn't really change. If I want to round 6134724 to 3 sig figs, that's going to be 6130000. It's not going to be 613. 6 million and 600 are very different. Make sure you keep track of it. If I want to round this to 3 sig figs, I'd say, okay. If I want to round this to 3 sig figs, we got not significant, not significant, not significant, sig, sig, sig. And so that's where I'm going to cut it. Okay? Any questions there? Well, apparently class must be over because the cat just left. And it's basically time anyways. I mean, I know I have 3 minutes, but I would be starting a topic I can't finish. So let's not do that like I did last class. And so we will end there. One last thing. I said this before. Most chapters I'm only going to lecture for 2 days. I'm going to lecture Monday and Wednesday, and then Friday will be practice problems. There's 2 exceptions to that. This is one of them. I will be lecturing on Friday where we will finish this chapter. Your first homework is due 1 week from today. I said homework's always due Wednesday nights. You do not have a homework due tonight because your first homework is on this stuff, and we're not even done with it yet. But you can get started if you want because, well, no, a lot of it's unit conversions, and we'll do those on Friday. But other than that, unless there's any questions, have a good day, and I will see you. Oh, that's what it is. Also, don't forget, your first lab will open up on Thursday at 3 o'clock. So tomorrow. So tomorrow at 3, you will be able to access your first lab. It is all about graphing and unit conversions. I admittedly haven't done unit conversions yet. It's the next slide. So you might want to wait, even though it opens on Thursday, you might want to wait till after Friday to do this one. Every other lab, I will have covered everything by the time it opens. This lab is just like that, just this one. But if you want to start looking at that, it will be open tomorrow at 3. But otherwise, now I'm going to leave. Have a good day.